Welcome to this new session of my course, Animated Multimedia Application Design, in which we will examine the applications of animated multimedia applications and define the concept of computer animation.
Animated multimedia applications are now integrated into almost every domain of computing. They play a crucial role whenever communication must engage multiple dimensions of human perception: visual, auditory, and even tactile. In the field of artificial intelligence, animated multimedia is used to enhance user interaction, support educational games, and improve interfaces for e-governance systems. In e-learning, it serves as a powerful tool for creating engaging and didactic courses, interactive demonstrations, and visual explanations that facilitate understanding. Regarding accessibility, such applications are invaluable for developing software and assistive technologies designed for people with disabilities, including those with partial visual impairment. They also contribute to performance optimization, particularly in decision-making and decision support systems, where dynamic visualizations can clarify complex data. In scientific research, animated multimedia enables realistic simulations, such as modeling chemical reactions or visualizing large data sets, thereby advancing experimental analysis and comprehension. In communication, it enriches traditional media by making information more expressive, interactive, and emotionally engaging. Finally, in virtual reality, animated multimedia provides the foundation for immersive environments that replicate real or imagined worlds, allowing users to experience interaction beyond the limits of conventional interfaces.
Computer animation refers to the digital generation of motion and transformation, allowing static objects or entities to be brought to life through simulated movement. Its primary purpose is to visualize changes and transitions over time, enabling a deeper understanding of processes, behaviors, and interactions that would otherwise remain abstract or invisible. By providing a dynamic representation of information, computer animation enhances perception, facilitates learning, and improves communication in a wide range of disciplines, from education and science to entertainment and virtual reality. The physical world is inherently dynamic, characterized by continuous change and time-dependent phenomena. Motion, transformation, and evolution are fundamental aspects of reality. To reproduce this natural dynamism in digital environments, animated multimedia seeks to simulate these temporal variations, creating convincing virtual scenarios that mirror real-world behavior. This underlying principle allows users to perceive virtual content not as static representations, but as living, evolving systems, thereby enhancing realism, immersion, and cognitive engagement. Human perception is strongly influenced by vision and hearing, both of which are highly sensitive to temporal variations such as movement, rhythm, and change over time. These senses naturally interpret dynamic information, allowing us to understand motion, continuity, and causality in the world around us. Computer animation leverages this cognitive capability by aligning digital sequences with the brain's natural processes of perception and comprehension. Through carefully timed visual and auditory cues, animations create coherence, guide attention, and facilitate meaningful interpretation of complex information. The animation creation process follows a structured sequence known as the animation pipeline, which ensures coherence between the technical stages and the perceptual experience of motion. The first stage, static definition, involves the design of the virtual environment and its components. This includes asset creation through modeling, texturing, scanning, photography, or importing ready-made elements, as well as scene setup, where objects are positioned, lighting is configured, and spatial relationships are defined. At this point, we obtain a static virtual world, ready to be animated. The second stage, dynamic virtual world, introduces motion and transformation. Through animation techniques such as keyframing, motion capture, procedural animation, or physics-based simulations, the scene gains temporal evolution. Here, the scenario or narrative logic determines how objects and entities behave and interact over time, resulting in a scenario-driven dynamic environment. Finally, the third stage, computer animation, or perceptual rendering, translates the dynamic scene into perceivable motion. During rendering, frames are computed and displayed to visualize the evolving world, while post-production adds synchronization, visual effects, and refinements that enhance realism and continuity. The outcome is the illusion of movement, perceived by the user as a seamless, lifelike experience.
Animation can be classified according to two main dimensions, the mode of execution and the mode of use. The first classification, by mode of execution, concerns how the animation is produced. In frame-by-frame animation, each frame is created or captured individually, as seen in traditional cinema, hand-drawn cartoons, or stop-motion techniques. This method provides full artistic control over every visual element, but requires intensive manual effort. In contrast, automated or procedural animation is generated algorithmically, relying on rules, physical simulations, or artificial intelligence to produce motion. Examples include fluid dynamics, the procedural growth of trees, or ragdoll physics in interactive environments. The second classification, by mode of use, refers to how the animation is delivered and experienced. Real-time animation is computed instantaneously, often in response to user input, as in video games, virtual reality applications, or simulators. It demands high computational efficiency to ensure fluid interaction. On the other hand, pre-rendered animation is pre-computed and stored as a sequence of frames, then played back linearly, as in animated films, advertisements, or cinematic cutscenes. This approach allows for greater visual fidelity, but lacks interactivity. Together, these classifications highlight the diversity of production methods and experiential modes that define contemporary animation across both artistic and technological domains.
Interactivity in multimedia applications refers to the system's ability to adapt its content and behavior in real time, according to the user's actions, inputs, and responses. Unlike traditional media, which deliver fixed and predetermined content, interactive multimedia involves a continuous feedback loop between the user and the system. The user's engagement becomes an integral part of the media experience, influencing how the system generates, modifies, or renders content. This dynamic exchange transforms the user from a passive spectator into an active participant, thereby increasing involvement, personalization, and engagement. A defining characteristic of advanced interactive systems is the tight synchronization between user actions and media rendering. In these contexts, the displayed or auditory content is generated or altered instantaneously in response to the user's input. For example, in virtual reality or VR environments or interactive games, head or body movements immediately modify the viewpoint and scene rendering, maintaining spatial coherence and immersion. Similarly, AI-powered assistants dynamically adjust dialogues, visualizations, and recommendations based on user interactions, creating personalized responses. In training simulators, such as flight or surgical simulators, each user action directly impacts the simulated environment, providing immediate and realistic feedback. This synchronized interactivity transforms multimedia from a passive communication channel into an active and adaptive system, significantly enhancing immersion, realism, and learning effectiveness. The realization of synchronized interactivity depends on a sequence of 4 interrelated technical components. Input capture. User actions are detected through devices such as controllers, motion sensors, eye trackers, or microphones. These inputs are continuously sampled and transmitted to the system in real time. Content generation. Based on the interpreted input, multimedia elements, graphics, animations, audio, or haptic feedback, are dynamically created or updated. Sophisticated rendering engines ensure that the resulting responses remain perceptually consistent and seamless. Processing and interpretation. The system interprets incoming signals using algorithms that may involve physics engines, gesture recognition, natural language processing, or AI-based decision models. Predictive algorithms can further anticipate user behavior, allowing proactive content adaptation. Feedback delivery. The adapted content is immediately rendered back to the user through visual, auditory, or tactile interfaces. Maintaining low-latency synchronization is crucial to avoid perceptible delay and to preserve the illusion of direct interaction, thereby sustaining immersion and realism.